Okay, so welcome to problem solving session for linear algebra. So today we will discuss problems related to week 10, that is problems related to orthonormal basis, Gram-Schmidt orthogonalization and orthocomplements. And I'm Siddharth Gambore from IIT Gandhinagar. So let us start with our first problem. And if you feel any doubt or if anything is unclear, please feel free to write it in the chat or unmute yourself and ask the doubts. Okay. We will start with question 1. So consider R3 with standard basis, standard inner product if 1 by root 2, 1 comma a comma 1, 1 by root 2, 1 comma b comma minus 1 comma 0 comma c comma 0 is an orthonormal basis obtained by Gram-Schmidt Gram-Schmidt process. So that is Gram-Schmidt orthogonalization method to the base 1 comma 0 comma 1 0 1 comma 0 comma 1 0 comma 0 2 comma 1 comma 0 of R3. Then find the value of A, B, and C. So what we are given is that this is base of R3 101 100 210, and when we apply Gram-Schmidt orthogonalization to this basis, we obtain this orthonormal basis 1 by root 2 1a1 1 by root 2 1b minus and 0c 0. So if this is the orthonormal basis obtained by applying orthogonal or Gram-Schmidt orthogonalization to this basis, then what are the values of ABC that we have to find out? Okay, so first let me go through quickly what is Gram-Schmidt orthogonalization process. So okay, so let V be an inner product space and suppose V1 to Vn be a basis of V, then we define this vectors W1 to Wn as below, where W1 is just V1 and W2 is, let me write it from here, W1 is V1, W2 is V2 minus inner product of V2 W1 by norm of W1 square W1, and W and so on. Wn is Vn minus Vn inner product of Vn with W1 by norm W1 square W1 minus Vn inner product of Vn with W2 and so on up to Vn Wn minus 1 by norm of Wn square Wn minus 1 square Wn minus 1. So we get this W1 to Wn, and these Wi's are orthogonal to each other. So what orthogonal means? That when we take inner product of W1 or Wi with Wj, where I not equal to j, then it will be 0. And if we take inner product of Wi with itself, then it will be a non-zero. So so this is how we define W1 to Wn. And then as I said, then W1 to Wn is an orthogonal basis, and such that span of V1 to Vk is equal to span of W1 to Wk for all 1 less than equal to k less than equal to n. Okay, and so now what we have is W1 to Wn orthogonal sets, orthogonal vectors to each other, but they are not orthonormal. So when we go from orthogonal to orthonormal, so orthonormal is just orthogonal set where norm of each vector is 1. So in order to get that orthonormal basis, what we just do is we divide by norm to each these elements, and we get this new set as orthonormal set. Or in fact orthonormal basis of V. Okay, so this is Gram-Schmidt orthogonalization process. So we start with V, and when we remove this, subtract this multiple of Wi minus 1 from Wi, and we obtain this orthogonal set. So that's what they are saying. So when we apply this Gram-Schmidt method to this basis, then we obtain this. So we have to find ABCs accordingly. Okay, so how we will start? So first is that for A, so let me write V1 to Vn's again here. So V1 is 1, 0, 1, V2 is 1, 0, 0, and V3 is 2, 1, 0. And we have to apply now Gram-Schmidt orthogonalization to this vectors. So first is W1, okay? So W1 is what? Just V1. So, and it is orthonormal. So whatever element, so let me just give them name. So this is beta. Let me call this beta, and this is now gamma. Then the first element of gamma, that is gamma 1, is what? W1 by norm W1, right? So it will be 1, 0, 1 by norm of 1, 0, 1. And this is standard inner product on R3. So norm of 1, 0, 1 is what? It is inner product of, let me write here square, 1, 0, 1, 1, 0, 1, and which is 1 plus 1, and then norm of this element becomes square root of 2. So therefore my gamma 1 is 1 by root 2, 1, 0, 1. So A was this here, the middle of, in the middle coordinate of first element, so which is 0 here. So therefore the A which they asked, therefore A is 0. Any doubts here? I mean, we just obtained this A value of A. Now for W2, what we have is, so WT is what? V2 minus norm of V2 W1 by norm of W1 square into W1. So V2 was 1, 0, 0 minus norm of 1, 0, 0, comma 1, 0, 1 by norm of W1 is root 2, which we already obtained, and W1 was this element. So W1 is here. Okay, let me highlight it. W1 is this element. W1 is V1, or let me write here, which is 1, 0, 1 in this case. And then we are taking orthonormal, which is gamma 1. Okay. And so norm of W1 is still this, and W1 is still 1, 0, 1. Okay, so it is 1, 0, 0 minus norm 1 square. So this will be 1 into 1, 0, 1 by 2. So then it becomes minus 1 by 2, 0, minus 1 by 2. Okay, and then now we have to find norm of this element is inner product of 1 by 2, 0, minus 1 by 2, 1 by 2, 0, minus 1 by 2, and it is 1 by 4 plus 1 by 4. So therefore, one by square root 2, because this is 2 by 4, which is 1 by 2. Any doubts here? So element W2 will be, or gamma 2 will be this W2, that is 1 by 2, 1, 0, minus 1, whole divided by 1 by root 2. So this root 2 goes up, and 1 by root 2, 1, 0, minus 1. Is it okay? And if you remember, the B was this. So B was again the second coordinate of this element, and which is again now 0. So therefore, B is equal to 0. So this is just calculation. You just have to understand the method and go on calculating, and we will get this. And the last one is gamma, or W3. W3, it is V3 minus V3 W1 by norm W1 square, W1 minus V3 W2 norm W2 square into W2. So we will calculate this separately. So V3 W1 by norm of W1 square into W1 is inner product of 2, 1, 0, 1, 0, 1 whole divided by 2 W1. So this is what? 2 by 2 into W1. So just W1, which is 1, 0, 1. Second element is V3 W2 by norm W2 square. If you have any doubt, please let me know. 2, 1, 0. And second element was 1 by 2, 1, 0, minus 1 by 2 by norm one by 2 and W2. So which is, here it is 2, 1 by 2, 1. That's it. 1 by 1 by 2. Into W2 is 1 by 2, 1, 0, minus 1 whole divided by, am I doing it correctly? Yes. So this is 1. The norm is 1. The inner product is 1. This is 1 by 2. So this is 2, 2 into 1. Am I missing something here? 1 by 1 by 2 into 1 by 2. W2 is 1, 0, minus 1. So it is 1, 0, minus 1. That's it. So W3 is 2, 1, 0, minus 1, 0, 1 minus 1, 0 minus 1, which is 0, 1, 0. And therefore, our last element was gamma 3 was 0, C 0. So this implies C is, so W3, norm of W3. So the gamma 3 is W3 by norm W3, but we can see that norm of W3 is just 1. So it is just W3. So therefore, which was 0, C, 1. So C is 1. Any doubts here? It was just calculation and nothing else. But still, how the process is carried and how we are dividing by norm and when we are considering. So first of all, when we do orthogonalization, we don't need to divide. So when I took W2 here, W1 here and W2 here, I did not divide by W2 by its norm. Its norm was 1 by root 2, but I did not consider it. I only subtracted, used W2 which I obtained here. Similarly for W1 here. And if I want to go ahead and calculate W4 for example, then I will choose W2 to be this element. Okay, and not something divide by its norm. Because the final elements which we get, we have to divide again by its norm. Okay, so when we are doing orthogonalization, just obtain the WIs first and then divide by their norm. I mean, whatever you get, just keep them as W2s. Don't carry them out again in the next calculation by dividing norm. I hope what I'm saying is clear to you. Otherwise, please let me know that it's not clear. So this was it about first question. So we wanted to find values of ABC. So A was 0, B was again 0, and C was 1. So second question is, let V be a finite dimensional inner product space check whether the following statements are true or false. Okay. First is that for V is equal to R cube, the set 1 by root 3, 1, 1, 1, 1 by root 6, minus 2, 1, 1, and 1 by 2, 1, 1, 1 is an orthonormal basis of R3 with respect to the standard inner product. Okay, so any guesses whether this set will fall orthonormal basis for R3 or not? Just by looking at it. You don't have to calculate all the inner products. Can we immediately say anything about this set? That whether this is orthonormal or not, or so on. So one thing which we used or proved in fact in the lecture also and in the last problem solving session also, that if we have orthonormal basis, then it has to be linearly independent. Okay, forget about the orthonormalness of a basis. If we have a, yes,
because last vector is
yes, so first and third one are linearly dependent, so this is not even a basis. So we don't, yes, so we don't need to even talk about its orthogonalness. Okay, so this given set, the given set, or let me, if I call this beta is equal to, this is beta 1, this is beta 2, this is beta 3, then if I want to write, so root 3 by 2 beta 1 plus 0 beta 2 plus beta 3 plus minus 1 beta 3 is non-zero linear combination of the elements of beta. Okay, therefore beta is not a linearly independent set. Therefore beta is not a basis of R3 and hence not an orthonormal basis of R3. Okay, it is not even a basis. Is it not even a linearly independent set? Okay, so it can never form a orthonormal basis, or yeah. So second one is, for V is equal to P2R. P2R is set of all polynomials in one variable with degree less than or equal to 2 with inner product P comma Q is equal to integration from 0 to 1 Pt Qt dt. The set, let me give them name now itself. Is orthonormal basis of P2R. So they are asking about the orthonormalness of this set. So to check this is orthonormal basis or not, we have to check like those 6 conditions, that Vi, Vj non-zero. Since they are 3, we have 3 possibilities: V1, V2, V2, V3, and V1, V3. And again, we have to check norms of each of these vectors using the inner product defined like this, integration from 0 to 1 and so on. So let us start checking. So first one, norm of V1 is 1 itself, and so, or let us first check about the 0 property, that V1 comma V2 is, so they are talking about orthonormalness. Okay, so it might happen that vectors are in inner product with each other, but their norms need not be 1. Okay, so when we check about orthonormalness of an elements, it's better to go ahead with the norms of elements first, and then to check for whether they are their inner product is 0 or not, because orthogonal set also has elements which gives 0 as inner product with each other when we take inner product of distinct elements, but their norms are not 1. So what they are asking here is about orthonormal basis. So it is orthonormal, so we have to first check the norms, because if once norms of this element are not equal to 1, then they are no longer orthonormal basis. So because if we go ahead and check that Vi, Vj is equal to 0 or not first, and you might get they to be all those like inner products to be 0, but when you then go ahead to check for the norms need not be 1, and then it will no longer be orthonormal basis. So first, when you start checking for orthonormalness, first go ahead and check with their norms. And first, and about the linear independence, So since P2R has three element, is vector space of order 3. So we have here 3 elements, and looking at them, we can clearly see that they are linearly independent at least, because first element is just constant, second one has degree 1 term, third one has degree 2 term. So this is at least, to begin with, is a basis. So we first check that this is linearly independent set and has 3 elements equal to the dimension of given vector space. And now we'll check the norms of these VIs. So to find the norms, we first have to find the inner product. So for V1, it is V1 comma V1. So norm 0 to 1, 1 into 1 dt. So it is 0 to 1, 1 dt. So it is just 1. Okay, or let me write 1 into, or just x running from 0 to 1, which is 1. Okay, so therefore norm of V1 will be square root of this V1 comma V1, which is 1. And now V2 comma V2 is integration 0 to 1, 2 root 3 x minus 1 by 2, 2 root 3 x minus 1 by 2. I'm just following, it's not x, here it is t, here also it is t. So this becomes 4 into 3 integration 0 to 1 t square minus t plus 1 by 4 dt, so which is 12 t cube by 3 minus t square by 2 plus 1 by 4t running from 0 to 1, and which is 12 into 1 by 3 minus 1 by 2 plus 1 by 4. And if you calculate this, it will be 4 minus 6 plus 3 by 12, and which will give us 1. So therefore, norm of V2 is square root of 1, which is 1. So V1 and V2 has norm 1. And now we'll check for V3. Integration 0 to 1, 6 root 5 x square minus x plus 1 by 6, 6 root 5 x square minus x plus 1 by 6 whole square. It's not x, it is t. So it is 36 into 5 integration 0 to 1 t square minus t plus 1 by 6 whole square dt, and which is 180 into integration 0 to 1. And when you take square of this, you will get something like this: x4 plus x square plus 1 by 36 plus 2 minus x cube plus x square by 6 minus x by 6, not x, t, t, t square, t. So which is 180 into t power 5 by 5 plus t cube by, or let me first write like this: integration 0 to 1 x power t power 4 minus 2t cube plus 4 by 3 t square minus 1 by 3t plus 1 by 36 dt, and which, so this is just calculation based, so even I can't do anything but just to calculate this, plus 4 by 3 t cube by 3 minus 1 by 3 t square by 2 plus 1 by 36 t from 0 to 1. And we can see that it will ultimately give us 1 by 5 minus 1 by 2 plus 4 by 9 plus this 0. We did not need to substitute here, because it will anyway give us 0. This is 1 by 6 minus 1 by 6 plus 36 plus 1 by 36. And if you calculate this, this is 180 into 1 by 180. Just trust me that it will be 1. Okay. It will be, if you calculate, it will be 41 minus 40 and 1 and so on. So norm of V3 again is square root of this V3 comma V3, which is square root of 1. So again 1. So at least all the elements have norm 1. And now when we check Vi, Vj's, we will also get that they are most probably 0. So 1 into 2 root 3 x minus 1 by 2 t minus 1 by 2 dt, which is integration 0 to 1 2 root 3 comma integration 0 to 1 t minus 1 by 2 dt, which is 2 root 3 t square by 2 minus 1 by 2 t 0 to 1, which is 2 root 3 into 1 by 2 minus 1 by 2, which is 0. Okay. Any doubts here? I mean, it's just calculation, but still, if you have any doubt regarding how we are doing this or anything of that sort, please let me know. Now for V2, V3. Or if you just don't want me to calculate, please let me know. We'll move ahead to next question if you want. 2 into 6 root 5 x square minus x plus 1 by 6 dt, which is when we take 12 root 15 integration 0 to 1 t cube minus 3 by 2 t square plus 2 by 3 t minus 1 by 12. So when we multiply these two polynomials, we will get this, and it will be 12 root 2, and when we integrate t power 4, 4 minus 3 by 2 t cube plus 2 by 3 t square by 2 minus 1 by 2 t from 0 to 1, and we get that 12 root 5 into this 1 by 4 minus 3 by 2 plus 2 by 3 plus 1 by 2, and it will be 12 root 5 and 3 plus 6 plus 4 minus 1 by 12, and it will give me 0, will be minus. And last, V1 and V3. Six root 5. So V1 was just 1, and V3 is 6 root 5 t square minus t plus 1 by 6 dt. So which is 6 root 5, 0 to 1. Or let me just directly do this. Minus t square by 2, 1 by 60, running from 0 to 1. And it is 6 root 5. 1 by 3 minus 1 by 2 plus 1 by 6, and it will again give me 6 root 5. 2 minus 3 plus 1 by 6, and it will give me 0. Okay, so all the conditions that we got, that norms are 1. Norms of V1 is 1. Norm V2 is 1. Norm V3 is 1. And norm of this V1, V2 is 0. V2, V3 is 0. And V1, V3 is 0. So these elements actually form orthonormal basis of P2R. Okay, and now a good question. Third part. So we are checking statements whether they are true or false. Orthogonal complement. Please let me know if there are any doubts of any set in V is a subspace of V. So this is a statement. A orthogonal complement of any set in V is a subspace of V. And any guesses? Orthogonal. We know the definition of orthogonal. Okay. Also, let me orthogonal complement. So let V be an inner product space. Okay. And the definition in the notes is given for any W, a subspace. But the definition actually need not need any subspace property of W. So that's why we can very well take this W to be a set. So then the orthogonal complement of this set or subspace W is denoted by W perp and is the set defined as W perp is equal to V in V such that norm of inner product of V with W is 0 for all W in W. So for all is very important. Okay, that for any given element it has to be from W the norm of norm, not norm. The inner product of V and W must be 0. So it is set of such elements. So they are asking for any given set whether this V per or this orthogonal complement of this set W will always be a subspace of V or not. Any guesses?
It's true because based on the definition of orthogonal complement which you stated, so V would be small v would be in bigger V. So
Mm-hmm.
and since W is in W, uh,
Mm-hmm.
the complement would always be in a bigger set V. So that's why it would be a subspace
Complement would be?
in V.
Yeah, that's okay. But whether it will be subspace. Subspace means it has to be closed under addition and
Yeah.
scalar multiplication. Yes.
Yes. Yes.
Yes. So whether it will be followed by this W orthogonal complement of W. So if I give two elements from orthogonal complement of W. So let me start. Let W be a subset of V. It's not subset. They are just talking about set. Any set of V. Okay. And then what is orthogonal complement? It is set of all such elements. So if I take any elements V1, V2 in W, then V1 plus V2 whether
But is W not already a subspace of V?
W
When
is
you
definitely not
when
be a subspace. And when we say orthogonal complement, it's not actually a complement of that set. It is orthogonal complement. It
yeah,
just, yeah.
no, I'm saying that when you stated that let W be in set V, then this W would always be a subspace of V because it would follow this properties, right?
They are asking whether W, the orthogonal complement
No, no,
of a
that's
set.
fine. That's
Yeah.
fine. What I'm saying is this would always be a subspace, right?
W?
Yeah.
No,
The,
no, it need not be.
okay.
W is any set. So if I'm, for example, if I'm talking about R3, okay, let us take this W to be this. Just an element, nothing else. That's it. And they are asking whether W per for this. So for this particular, is subspace or not. This is the question. They are asking for any given set and not just a subspace. Now, what is your guess? See, in the question, they are talking about any set in V, not subspace.
I think subspace, ma'am.
Sorry,
W perp
it
is
is
subspace.
subspace. That is your guess.
Yes, ma'am. I guess. I
Yes,
have
yes.
I have reason because V perpendicular to W, then scalar multiplication of V also perpendicular to
Yeah, exactly. So
W.
you are saying this property that if such a thing is happening, that if this is there, okay, then this we have to check whether this belong to W or orthogonal complement of W or not. Then what are elements in there of this form? But we know since we have inner product on V, so V is inner product space, so this splits. And as sir said that this will be 0 because V1 and V2 in W. Oh, not W. In orthogonal complement of W. Okay, so sorry. So just because I wrote here W, you were saying that W is subspace. Was that because of my writing mistake? Hello, sir. Hello.
Ma'am?
So what I was saying, sir, since I was saying W, V1 and V2 were in W, I had written W here. That's why you got confused.
No. W perp. I am saying W perp is subspace.
Okay.
Uh,
Okay. And then
Since
that's
V
okay.
V belongs to W perp.
Okay, yes. And now similarly for constant, so if C is in the base field and V is in W per, then this or not W, not V in W per, then CV comma W will be, we know is V comma W, and since it will be, and so therefore this W per is subspace of V. Okay, so W to start with need not be subspace, but W per, that is orthogonal complement of W for any given set W, will always be a subspace. Is there any doubt here about set and subspace and so on? So even if we start with the set,
But
that
when
need
we,
not.
sorry, but
Mhm.
when we take W complement, so we do the inner product of V with W.
So
Can you scroll up, yeah, on the
yeah.
definition? Sorry.
Mm-hmm.
So we do an inner product of V with W. So if
This V is small v.
this V small
Mm-hmm.
v,
Mm-hmm.
so and W is in W.
Mm-hmm.
So is it necessary that I'm trying to say is that it would have the same dimension? May you say that uh, since in your given example, W had a dimension of 1 in R3,
Mm-hmm. Mm-hmm.
but say V would have a dimension of 3.
Yes.
So how would the inner product work? So because you would need the same dimension to work to do the inner product, right?
Dimension means
At least you would have the same elements, right? Or this set
any
would be of
set
3
means not
vectors.
any set. Any set in V. Set in V. Oh, okay. I mean the W must be inside V. I mean R3, what element R3 has? R3 are of the form A, B, C such that, okay, these are in R, right? And this element W is inside R3. And what I am saying is my W is 1, 0, 0. So what definition of W perp will be here? It is all those V in R3, since we are in R3, such that inner product of V comma 1 comma 0 comma 0, or let me write W for all W in W just by definition, but all W in W per all W in W means what? There is only one element in W. So which is V comma 1 comma 0 comma 0. Oh, here it has with 0. Okay. So that's it. So this is the definition of W or orthogonal complement of W for any given set. For example, for this specific set here I am talking about. So this is a set. It contains only one element. This is not subspace of R3 since, or let me write 0, 0, 0 doesn't belong to W. Only one element. Is it okay, or there are still doubts?
No, there's no doubt. I'm just trying to comprehend.
Okay, sure.
Okay, it's fine. We can.
Yeah, it is not W in entire R3. It is like we are collecting only those V's in R3 such that inner product with W is 0.
So we'll take a small v as v equals to ABC, and you'll take inner product of
Yes, for
ABC,
example, let
comma
us just
1, 0,
calculate.
0.
Yes, so let us calculate because it will clarify then. So let me specifically write A, B, C in R3 such that inner product of A, B, C. So we are in standard inner product for now, and we will see how things goes here. So A, B, C such that A plus B into 0 plus C into 0 is equal to 0. So it is like A, B, C such that A is 0 and B and C could be anything in R3, right? Because they are independent, because anyway they are getting multiplied with 0. So it is of the form 0 comma B comma C in R, B comma C such that B and C are in R3. And now this is subspace of R3, right? This is subspace of R3 of dimension 2.
Hmm.
Okay, but the W which we started with was not subspace. It was just a set containing only single element 1 comma 0 comma 0. But its orthogonal complement is the subspace. That's what this statement says.
Okay.
That
Now it makes
orthogonal of
sense.
any set in V. So we are starting with a set which need not be subspace in V, but its orthogonal complement is always a subspace. Okay, is
Because
it
you would
clear?
have a multiple elements there, and it's
Yes,
just single
exactly.
element. Yeah.
Yes,
Okay.
yes. Okay, now is it clear?
Yeah. Yeah.
Okay. Where so let's move to next question. And they are saying that if W1, oh no, okay, V1, V1, V2, Vn is a basis of V, then for any x in V, we have x is equal to summation I from 1 to n x comma vi. So they are asking whether this is true. V1, V2, Vn is any basis of V, any basis. Then for any x in V, whether we have this expression or not. That's what they are asking. Whether this always hold for any given basis of V. There are no conditions on V, on the basis. It's just a normal basis. Any guesses? Okay, so if we remember from the lectures, so we proved such kind of statement for orthonormal basis. So if we have orthonormal basis, then we can sure write such expression for given any element x in V. But now they are talking about any given basis. So the statement which we proved for orthonormal basis in the lectures, whether this statement is true for any given basis or not, that's what they are asking. Okay, so an answer to this is false because this need not hold for any given basis of a vector space. So let us take this V to be R3, and this is basis of R3. Okay, so this is basis of R3. Okay, you can just check, and then we just choose x is equal to the element of basis itself. Okay, and for basis at least whether this will hold or not. Okay, so then this x is this, and this LHS, sorry, the RHS which we have here is summation I from 1 to 3. So since we are in R3, it will be 3. X is 1, 0, or let me write this V1, V2, on V1, V2, V3, comma Vi into Vi. So what this will be? This is inner product of 1, 0, 0 with 1, 0, 0, since V1 is this same element, into 1, 0, 0 into 1, 0, 0, plus second is 1, 1, 0, 1, 1, 0 into 1, 0, 0, plus 1, 1, or am I making some mistake? Okay, I am changing the sequence, so it must be 0, and that's okay. 1, 0, 0. It won't change anyway the final calculation because symmetry is there in R3. So, but still. So it will be what? Here inner product is 1, 1, 0, 0. Here again the inner product is 1, right? It will be 1 into 1, 1, 0. Plus here again inner product will be 1 and into 1, 1, 1. And if you add this element is 3 to 1, which is definitely not equal to x which we started with, or 1, 2.0. So this holds only when we have orthonormal basis. Even for orthogonal, this need not hold. Because see, if we have orthogonal such that norm of Vi is not 1, that in that case, suppose even if we take orthogonal set. Okay. For example, if you check this set, V is equal to 1, 0, 0, 0, 2, 0, 0, 0, 3. This is orthogonal, okay? Orthogonal means Vi Vj, inner product of Vi Vj is 0 for any Vi not equal to Vj. But again here, if I am to write this element 0, 2, 0, then it will be what? 1, 0, 0, 0, 2, oh, as per the given question, let me write it as it is, plus inner product of 0, 2, 0, 0, 2, 0 into 0, 2, 0 plus 0, 0, 0, 2, 0, 0, 0, 3, 0, 0, 3. And now this will be the first one becomes 0, so it's 1. Third one also becomes 0. Now the second one, if you go and calculate its inner product, it is 4 into 0, 2, 0, which is 0, 8, 0, which is definitely not equal to 0, 2, 0, right? Oops, it's not this. It is summation I from 1 to 3. Let x is equal to 0, 2, 0. Then inner product of x, vi, where v's are this. Okay. So is it okay? So we strictly need to have orthonormal basis in order to have this kind of expression that x is equal to summation I from 1 to n. It does not even hold for orthogonal basis, as we just saw here. This is orthogonal basis, by the way. This is set of orthogonal elements and has dimension 3, linearly independent. But this also does not give this kind of expression for any given element x in vector space V.
Can we say because we are in R3, we kind of your inner product would be your dot product. So
Yes.
so if I say inner product of x comma v1 into v1 would just be x into v1 square.
No. That's not what it is.
No, I'm just asking because
No,
your inner
it's not.
product
It's
would
not.
be a dot product in that case, right?
Because when we do this, when we write this, so let me just do this. So what you are saying is when we write this, comma, 1, 0, 0 into 1, 0, 0. So this is some element in our base field. So this is the entire thing is scalar multiplication with scalar inner product of 0, 2, 0, 1, 0, 0. I hope. So this is some scalar which we are multiplying with this element. So it is not just like we can just, if you are doing this and then multiplying it by this, that won't work. That is wrong. So when we do this inner product is some scalar in our base field F. So in our case, it was R. And then we are scalar multiplying with it with this element 1, 0, 0. Is it okay?
Yeah, it's fine.
Yeah, because that's what we did here. Because here inner product was 0. Then again here inner product was 0. Here inner product was 4. And then multiplied with this. So this was scalar multiplication here, if you see. Okay, 4 into this element for the second term here. Because if we had done this first and then this, then it would give us like something different. Because here inner product will be 1. And 1 into this thing will be 0, 2, 0. But it's actually 0, the first term. I hope what I'm saying is making sense to you. Yeah. So that's what I was saying. Okay, so I hope it is clear now that this this expression holds only when our basis is orthonormal basis. This does not even hold for orthogonal basis. Okay, so let us go to next. Yes, sir.
Suppose we take x is equal to vi.
X is equal to
vi.
vi.
One of the basis vector.
Yes, that's what I took here, right? For this, the basis element itself was v. Yeah.
I
This
will try
was
to
v2 here.
prove the above statement.
Old statement here.
Yeah.
Yeah.
I will try to prove both statement, I guess.
This one or the even
I
the
think
previous
this is
one?
counter example.
Yes.
How to prove this statement, fourth statement?
It's false, actually. So we can't actually prove this. It won't be true. It's false.
Okay.
We can't, we just gave counter example. So this statement is not true. So we can't prove this actually. Because if we start, we can't show this. Because see, this example itself gives us that statement, can't hold. So we can't prove this. Yeah. In this example here, this VR3 And this X element, an element from basis itself can't be written like this. So forget about any given V in X in V, okay? So this statement is not provable because it's false. We just gave a counter example. And okay, is it?
Sorry,
Yes,
one
sir.
second.
Yeah, no problem.
If you can scroll up. Yeah. So
Yeah.
we actually are saying that it's a linear combination, right? If you're considering X
Yes.
comma Y in a product, then it's a linear combination and it
Yes,
has to be
exactly.
equal to X. But since your base, it's a basis of linear combination, so it has to be 0 because or else you lose independence.
Sorry, sir. I couldn't understand the last part.
So what you're saying is if I can write any vector in terms of basis with your scalar, non-zero scalar.
So
No,
what this
but I was
statement says is, yes.
what I was thinking is that if I write my basis as linear independence, then all my scalars have to be 0, right?
They are linearly independent, no doubt. They are linearly independent elements, but basis means what? We can express any element in the linear
Yeah, okay, okay.
combination of the
Okay.
basis.
I was thinking other way
Yes.
around. Yeah, okay.
Yeah. Okay. So the basis element itself has to be written in terms of the elements from the basis. Okay, so for example, this 1, 0, 0, this is the basis. For example, this element. If I want to write it as a linear combination, then V2 will be what? 0 into V1 plus what? This 1 into V2 plus 0 into V3, right? So V2 is written as linear combination of elements of basis. It is linearly independent, definitely. The V1, V2, Vi's are linearly independent. Okay. I mean, I hope I'm making it clear. Okay. So if you have any doubt, please ask. Otherwise, we will move to next question. If now they're asking about this set, if S is this set, V1 to Vn in V satisfies the condition Vi, Vj is equal to 0 for all I not equal to j, and Vi is non-zero for all I. For all I, then the set S is linearly independent in V. So this is the question. So they are asking that S is such that inner product of each element with other is 0 whenever I not equal to j and Vi is non-zero. Okay, so this Vi is non-zero condition is important because see, if we choose these elements, for example, 1, 0, 0, 0, 2, 0, and 0, 0, 0. So in this case, inner product of Vi Vj is 0 for any given I not equal to j. But this set is not linearly independent. Okay, so this Vi non-zero condition is important here. Otherwise, the set will be linearly. We can just add 0. Still, the inner product of distinct elements will remain 0. But set will not be linearly independent. Okay, so this Vi non-zero is important condition here. And now what is your guess? That if S is some set satisfying this condition, then whether this set S is linearly independent in V or not. And we did, I guess, the same kind of question last week also. Okay, so, and we already proved that this is true. I mean, I was completely proving the calculation of Vi is equal to inner product, but sir said that we already have proposition we state that if vi is taking inner product with all the linear combination of other element will again give us 0 and so on. Okay, so we'll do that again this week. So let a1 v1 plus a2 v2 if something of this sort is 0 with at least one of the ai's non-zero. So then we can write vi is equal to a1 ai v1 plus ai minus 1 ai v I minus 1 plus ai plus 1 by ai vi plus so on up to not vi plus 1 plus an by ai vn. Okay, then we have this proposition which state that let V be a inner product and inner product space over F, and suppose V1 to Vn are vectors in V which are orthogonal to W in V, then any linear combination of V1 to Vn is orthogonal to W. Okay, so since Vi, Vj is 0 for all I not equal to j, so therefore we get that Vi, this element here which we obtained, that Vi, I V1 plus ai minus 1 by ai Vi minus 1 plus ai plus 1 by ai Vi plus 1 up to an by ai Vn. This becomes 0 because the W here or this element here is just linear combination of all I not equal to j element or in the set S. Okay, so this becomes 0. Then by definition itself, if some Vi, Vi is 0, then by the definition or properties of norm, we know that then Vi is 0, which contradicts the fact that Vi is non-zero in S. Okay. So therefore, such linear combination is not possible. So therefore, this set is linearly independent. Therefore, no non-zero linear combination of element of S can give 0. Therefore, S is linearly independent set. Any doubts here? Okay, so this statement is true and we kind of just proved it. This is the proof. Okay, or if you like the language like this, suppose S is linearly dependent, then and so on. And then we have this proposition, contradiction we obtained, and therefore combination. Okay, any doubts here? We did the same calculation last week as well. So still. If not, then we will move to how did we get the final implication. This, then this part, I guess you're asking. So what we got here, this vi is 0. So, because we have this vi into vi is positive when vi is non-zero. This is the definition, or this is the property of inner product. Or if you don't like this, which is contradiction, as vi is non-zero and vi comma vi is greater than 0 by the property of inner product. Is it okay? Yes, vi is 0 actually. Because this statement actually gives that vi is 0 and so on. Okay. So
Sorry, one observation.
yes,
I'm just
yes.
clarifying my doubt also here. But
No problem.
since we have expanded Vj, uh, and when we do the inner product, then we would have to prove that A1 upon AI is the complex conjugate, right?
Wait, vi comma vi is equal to, and now
Uh, So the first term, when you take Vi comma A1 upon AI V1 inner product, the first inner product, then you would have to prove in this case, because you have expanded the second term, right? Uh,
okay.
so you would have to prove that this particular A1 upon AI is complex conjugate.
Or we can just
Yeah,
take this
that's what I'm trying to say, that instead we do this, because or else we would have to prove that it's a complex conjugate, and
complex
it's
conjugate. Yeah. So, but I guess this one is better in that case. But
yeah,
yeah.
yeah, it is, but I'm just asking that
Yes,
what
yes,
I was thinking is
definitely.
correct,
If
right?
we have to do that, I mean, properly, if we go and expand, then we have to do that complex conjugate and stuff. But
Okay. If
yeah,
you do this way, then we don't have to, right?
then we don't have to. But yes, when we, even when you do that, the complex conjugate and so on, you will take common as conjugates. But still, the inner product of this vi and vj still will be giving us 0.
Will
So
be
the
zero, yeah.
yes, but the final conclusion or the final answer will be 0. But yeah, but the coefficients will be conjugates of the whatever scalar we have here. Definitely, yes, that's true. Yes. But if we do this, then we don't need to do the inner, why we need to, okay. So why we were talking about conjugates is because vi comma vj, if we do, then, or cvj, then it is c into c conjugate vi vj. This is the property. And what we had written here was, also let me not write the all everything, but let me just write first two terms. So if we have this vi comma a1 comma ai v1 plus a2 comma v2 comma ai, then if we split them, then vi comma a1 by a, then, or let me just do everything properly, a1 comma ai v1 conjugate v1 plus a2 comma ai, because when we do write the definition of inner product, then we have linearity only in the first coordinate. Okay, but when we prove that, for when we do the same calculation for second coordinate, then addition, it remains symmetric. Addition gives us linearity in the second coordinate, but the scalar multiplication not fails, but so let me just write, then it will be clear. Then it will be a1 by ai v1 plus vi comma vi plus, so add conjugation splits over addition, so v2 comma vi. Then when we take common, something like this, then it will be v1 comma vi plus entire conjugate a2 comma ai into v2 comma vi conjugate, and then it becomes a1 comma ai into v1 comma vi comma v1 plus a2 comma ai conjugate vi comma v2. So what they are saying is that a comma b plus or v comma w1 plus w2 when we do, then it is v1 comma v comma w1 plus v comma w2, but v comma cw is c conjugate v comma w. And since here what I had written earlier, it was vi comma this addition, vi comma this addition, the scalars will give us scalar will be conjugate of whatever we have here. Now is it clear? Here when we calculate, then scalars will be conjugates of whatever we have. Okay, so that's why. Okay, so I hope, okay, great. So we'll move further then. Question third. So let S is equal to sin t cos t 1 comma t and V be a real vector space. So we are in real now and we don't have to worry about conjugates now. Vector space V is equal to span S considered as a subspace of the vector space of real valued continuous functions C01. Now consider the inner product space V with respect to inner product defined by, finally we are at inner product. So f comma g is integration 0 to pi f of t g of t dt for f comma g in V. Okay. So after applying Gram-Schmidt orthogonalization to S, we get the set this f1t, f2t, f3t and f4t. So since we started with set of 4 elements, the set an orthonormal basis of V. So they are saying that if root pi by 2 f1 of t is a sin t plus b cos t plus c into t, then find a plus b plus c is equal to what? This is the question. We have to, so they have given S like this. S is this, inner product is this, and this now f1, f2, f3, f4 are orthonormal bases which we will obtain by applying Gram-Schmidt orthogonalization to this set. So it has 4 elements. So if we have such expression, then we have to find the value of ABCs. Okay, so let us start with F1. So what is F1? So F1 is, so first W1 will be just sin t. Okay, W1 is sin t. So therefore f1 will be what? Sine t by norm sine t. Okay. Then if I want to write it, so I have to find norm of sine t then to find f1, because see here I am writing f1 as a linear combination of sine, cos and t. So I have to find what is f1t so that I can talk about this linear combination. Okay. And this is by definition is 0 to pi sine square t dt. And then this will be 0 to pi 1 by cos 2t, or if you sine t into sine t dt, which is integration 0 to pi sine square t dt 1 by cos t, and which is 1 by 2 1 minus integration 0 to integrate 1 minus sine 2t by 2 from 0 to 1, 0 to pi. We are calculating 0 to pi. So this is 1 by 2 into pi minus 1 by 2 into 0 minus 0, which is pi by 2. Okay. So once I have this, and since it is orthonormal basis, using this, let me show you this, which we just proved. This statement actually is true for given statement. So if I write this, then f1 of t becomes square root of norm of sine t is square root of this pi by 2. So therefore square root of pi by 2 f1 of t, or if I'm to write f1 of t is just sine t by square root of pi by 2, and this will just give me square root of pi by 2 f1 of t is equal to sine of t. This is there, so I can just write this as 1 into sine t plus 0 into cos t plus 0 into t, right? Because I wanted to express f this like this, right? f1 was of this sort, then therefore a will be what? 1, b will be 0, and c will be 0. And why I could do this? Because this set sin t, cos t, 1 comma t is basis of v. So that's why I could write this. So I don't need to find all this f1, f2, f3, f4 and go so on. Just knowing the fact that this is basis, because any given element from the vector space can be uniquely written as the linear combination of basis elements. So this is basis. So if I can write this element is, so this f1 to t, this belongs to v, which can be written as 1 into sine t, and sine t is basis element. So this is only one way of writing this linear combination. This square root of pi by 2 f1t as 1 into sine t, 0 into cos t, or just to be complete, we can just write like this. So this we don't need, and 0 and so on. So is it okay? And therefore a plus b plus c becomes 1. Any doubts here? Just a calculation, and using the fact that this sine t, cos t, 1 and t is a basis. So they are linearly independent, and Any element can be written as linear combination of basic element in only one way, uniquely. Any doubts here? Please let me know, like how things are happening, or how we are not doing anything else, or why did we stop at this stage to obtain ABC and so on. Any doubts, please let me know. Otherwise, we'll move to next question. Let V be a finite dimensional inner product space. A and B be subsets. Okay, we are again in subset, so we are talking about only sets and not subspace of V. And now check whether the following statements are true or not. Okay, so first statement is that if A is contained in B, then the orthogonal complement of B is contained in orthogonal complement of A. So any guesses for this statement? Whether this is true, false, or anything? So this, we have to check whether this statement is true or not. So first, let me write the definition of orthogonal complement of B and A. Okay, what is orthogonal complement of B? This is all those V in V such that V comma B is 0 for all B in B. And what is orthogonal complement of A? It is all those V in V such that V comma A is 0 for all A in A. Okay, so if any element, for example, if V is in orthogonal complement of B, then this V comma B is 0 for all B in B. But A is contained in B. So this, for example, if this is B and this is, no, yeah, and this is A. So this V here is satisfying something for bigger set. And now we are talking about something in the smaller set. Okay, so if something is satisfied for bigger set, elements for the bigger set, then it will be satisfied for the elements from the smaller set as well. So that is what this statement is, which is contained in B. Okay, so therefore this V belongs to orthogonal complement of B. Therefore, we have this thing. Any doubts here?
No, man.
Okay.
Clear. But
Okay.
reverse inclusion not true.
No, reverse is not true.
Yes.
And can you give me an example that if orthogonal complement of B is contained in orthogonal complement of A, then A is contained in B. Can you give me counter examples? As you correctly guessed that it is not true. The converse of this statement is not true. Okay, so this statement is true. So we are now talking about its converse. And sir already said that it is false. So let me write false here. But I would like to see a counter example for this. Any counter examples?
Ma'am,
Yes.
A per 0 set.
Okay, if A is a 0, okay, then A orthogonal complement will be entire V. That is okay. And B could be anything. Let B be any subset of V in that case. Whatever B perp is, it is still subset of V which is A perp. So this is not contradiction. In this case, this P perp is contained in A perp, but A is not A, and A is also contained in B. So this is not counterexample actually. Is it okay that this is satisfying and this is also satisfying? 0 is in inside. 0, which is A, is contained in B. So this is not counterexample. This is in fact satisfying the given statement. Can you give me the counterexample? That is, orthogonal complement of B is orthogonal complement of B is contained in orthogonal complement of A, but A is not contained in B. So what I want is, we want orthogonal complement of B is contained in orthogonal complement of A, but A is not subset of B. This is what I want to have counterexample. Any guesses? Or no guesses? If there are no guesses, then I can give you
Suppose assume B contained in A.
V element.
No. B contained in A. Set.
V.
Reverse inclusion assume.
But V, I mean.
No,
V.
B contained in A.
Okay. Then. But if V contained in A, then by above statement,
Yes,
A, this will be contained in this. But I mean, again, we are in the loop now. We are just changing the names of A and B, but we are, landing on the first statement, which is true, which we just proved. So, counterexample, specific counterexamples, like V is equal to R2 or R3 or set of functions, whatever you like, inner product, and then counterexample should be specific. When it need not be specific as specific, but has to have something. Okay, so let us start. Okay, so I guess there are no guesses. So I will just let V be R3 and standard inner product. And you can also do this in R2 as well. But I am doing this in R3 because I just wanted to have concrete things as such. So it is start with this. So standard inner product on R3. And so let A be this set 1, 0, 0. Just a set containing one element. Or let me write cardinality of A, or set containing one element, because someone might consider this as dimension. So one element, and B with this. Or we'll reveal the B afterwards. Let us find orthogonal complement of A. It is set of all these A, B, C in R3 such that inner product of 1 0 0 with A B C is 0, right? And we don't need for all V in A, for all W in A and so on, because the only element is A, and A comma B comma C in R3 such that A is 0. So this is just a set which we earlier obtained, B comma C such that B comma C in R3, right? We do not have any problem till now, right? It's okay. A is just element, set containing one element, and or orthogonal complement of A is this set. And now let us take B to be this set. 2, 0, 0, 0, 3, 0. Okay. And then what is B per? It is A, B, C in R3 such that, let me just see what I wrote here. Or let it be. We will calculate it such that inner product of 2, 0, 2, all for this, let me write W comma or V comma W. V comma W. I mean, we are in R and R3, so conjugate is symmetric, so we don't worry about or I mean, you will get what I'm writing here. Maybe it is a bit clumsy, but yeah. For all W in B. For all W in B means what? Since B has only two elements, it is specifically A, B, C. Please understand that we are in R, so we don't care about which coordinate we are keeping the elements and so on. And ABC such the and, okay, it should satisfy both this inner product to be 0. So what does this mean? A, B, C in R3 such that 2A is 0 and 2B is 0, 3B is 0, right? So this and C could be anything in R. So this is A, B, C in R3 such that A is 0, B is 0 and C in R3. Okay, so this is just 0, 0, C in R3 such that, I mean, no such that is required, but yeah. So in this case, now A per orthogonal complement of A was this 0, B, C, where B, C in R, and B per B complement, B orthogonal complement of B is this set. So clearly, this B per is contained in A per, right? No doubts here. But A is not contained in B because A is what? This set 1, 0, 0, and B is what? 0, 2, 0, 0, and 0, 3, 0. I mean, none of them is contained in other. They are completely disjoint sets. But their orthogonal complements are contained in one another. Or orthogonal complement of B is contained in orthogonal complement of A. Is it okay? This counter example, is it?
Yes, okay. Okay, ma'am.
Yeah.
Thank you.
So this. So the set is playing a role here. Okay, if I am to take subspaces, for example, if I take subspace generated by A and subspace generated by B, then subspace generated by A is contained in subspace generated by B, set B. Okay, in that case, that those subspaces, for example, if I call them WA, WB, those subspaces will not give me counter example, because in that case, this WA will be contained in WB. But when I talk about sets, that's when I'm getting the counter example. Okay, I mean, please try try to understand that thing, because it will be clear from the next statement that first, that is A is equal to A per. That is orthogonal complement of A. Okay, for the subspace, both statements will be true. Yes, yes, I guess for the subspace it will be. I think for subspaces. Yes, for subspaces it will be true. Okay, we will see why. Or we will understand why. Because see, A contained in B, then B per contained in A per. Okay. And if I again take this, that complements the B per contained in A per, then B per is contained in A per, and so on. So let me just keep this on hold for a while, and we will first see this. I mean, those who just got an idea will know whether this statement is true or not. A is equal to A per, or orthogonal complement of A, and then we again take orthogonal complement of A. Whether this is true. Okay, so this is again false. We will see why. I will also give you counter example. So a small counter example. Let us take A to be this set. Again, I'm talking about set in R2. Okay, so my V is R2. Then what is A per, or orthogonal complement of A is just A comma B in R2 such that okay, we don't need for all and so on here. So it is just A comma B in R3 such that A is 0. So it is just element of the form 0 comma B in R, oops, not R3, R2 such that B is any element in R. Okay, so it is just this set. And now A per is what? It is all those, let me write C comma D in R2 such that C comma D into 0 comma B, right, is 0 for all B in R. I hope you understand this when I'm writing this part. If you have any doubt, please let me know. I assume that you are understanding what I wrote there, such that C into 0 will be 0 and B into D is 0. Since B is running over R, it is C comma D in R2 such that D is now 0. So this implies it is C comma 0 in R2 such that C in R. Okay. But this is not equal to A because A was just this element. Okay. Any doubts here? This is counter example for this thing. And we will go back to that complement, the converse true for vector subspaces in just a minute. But this is understandable, right? That A need not be equal to A per. That is orthogonal complement of orthogonal complement of A. Okay. And the fifth one is that if A is equal to A per, then A is subspace of V. And what is your guess for this statement? If we are to talk about, because see here, when I started with this A perp and I again took perp of A, I got a subspace, but note that A perp is a subset of V, then A perp is a subspace of V, right? Because we just proved that for any given set, A perp is always a subspace. Okay, so this is subspace of V. Then again, A is equal to A perp is subspace of V, right? We proved earlier. So this is exactly, I mean, this statement is that A is subspace of V. Okay. Any doubt here what I just wrote or anything confusing? Because we proved that for any given set, its orthogonal complement is always a subspace. But so we can take that set to be A perp, that is orthogonal complement of A itself. And its orthogonal complement is a subspace. But what is that? It is A again. So that gives us that A is a subspace itself. Okay, and now we do this. The statement, let me write this, that if B, A is contained in B, if and only if, or let me like, if and only if B perp is contained in A. So this statement is in general false. We can see the counter example for the converse implication. In, I guess, third was the one where we gave counter example, right? Not this for third. Second one. In 2 for the converse implication. But for subspace, now the things change, because now if let A and B be subspaces, or let me just write W1 and W2, because to be clear, W1 and W2 be subspaces. Then if W1 is contained in W2, then this is anyway true, right? W2 perp is contained is W1 perp, right? And now I work with this W2 perp, then W2 perp is contained in W1 perp is what we have. Then again we get this reverse inclusion, that W1 perp is contained in W2 perp. Okay. But since W1 and W2 are subspaces, using this, that A is equal to A perp, then A is a subspace, then we get W1 and W2 here. I hope I'm making sense, I guess. I don't think this will hold in general, now that I think of it. Because what we have is that if A is equal to A perp, then it is a subspace. But just because the converse of this statement, I don't know whether this hold or not. Okay, so converse of this, so this is true, definitely. But I am confused about converse here. If converse of this statement is true, then we are okay. But I doubt whether the converse of this statement is true. Any cases here or any input anyone would like to give? That this is true or false or converse was okay, not okay. Ma'am, but it was given condition. Yeah, I mean, it is given that, okay. Still, so W1, W2 are subspaces. So the statement is if A is equal to A per, then A is subspace, okay. But whether A is subspace, then if A is equal to A per, that is the question. Because if this is true, if this statement, if true, then if I call this star, then star holds and we get the required implication that this statement A contained in B, if and only if B per contained in A per is true for vector spaces, but we don't know about this, whether this is true or not. Or let me do this. We don't know this, whether this holds. Okay. If this statement holds, then we are okay. I will, okay. So I will check this and I will let you know in the next lecture or next problem session, or maybe I will put it in.
No, I think that is false.
It is false. Can you please, sir, give me a counter example? It would be really great.
Your counter example from previous problem.
Okay.
5. Take it.
Okay.
A is a subset of R2.
Yes, exactly. See, we got the counter example. But no. But they are saying already given that A is a subspace, then A per is equal to or not. We did not start with the subspace here, right? This is not subspace. This is just
Suppose
set.
A is not a subspace, contradiction proof.
Then that is anyway is true. No, the statement is if A is subspace, then whether A is equal to A per or not. That is the question. We are not talking. So we already have here, right? That if A is equal to A per, then A need not be subspace. That is, sorry. If A is not subspace, then this anyway does not hold. That is there. But now we are starting with the subspace and we are talking whether A per will always be a subspace. I think I'm confusing. This we know. Okay, if it is equal, then it is subspace. But if we start with the subspace, do we end up getting that A is equal to A per? That is the question. If we don't start with A per, then we are not even talking about this statement in that case. I hope I'm making sense.
We prove negation statement, no?
Negation means you are saying? If negation is true?
We will check.
Yeah, exactly. That's what I was saying. That we need to check actually this. This is not that trivial, which I just felt that it is. Or it may be trivial, but at this moment I am not getting the feel of it. So I will definitely let you know in the next problem solving session, or I will put it in the discussion forum. But at this moment, even so, this statement also becomes now questionable. Whether, this, if and only if, whether this is true or not. Whether true or not. We will discuss this. In meanwhile, if somebody gets counterexample or can prove this, please feel free to inform us. Okay, so let us solve this question. Okay, let us do this one only. It will take some time, but it is good question. Okay. M3R with the inner product A comma B. We actually proved this, that this inner product, this forms actually inner product in M3R. Okay, so we are in M3R now. Then the dimension of orthogonal complement of the set S is equal to A in M3R. So we are in 3 cross 3 matrices and such that trace A is 0. So now the subspace, we are starting with the subspace. Subspace S equal to dimension. We have to find the dimension of orthogonal complement of this subspace S. Okay, so so how to start with this? Okay, so again this S perp is what? All those A in M3R, or let me write B in M3R, such that inner product of A comma B is 0 for all A in S, right? So if I am, so let us calculate how this inner product look like, okay? If I have this A comma B, okay, A is Aij, I from 1 to 3, I comma j from 1 to 3, and B is from Bij, I comma j from 1 to 3. Okay, and this A is in S and B is some element in M3R. So let us see how this look like. This A comma B is trace of B transpose A. So forget about trace. Let us see how this element B transpose A look like. So it is B11, B12, B13, right? So we are taking B21, B22, B23, B31, B32, B33. Okay, this is B transpose, right? And A will be A11, A12, A13, A22, A21, A22, A23, A31, A32, A33, right? There's no doubt in here. Okay. And then multiplication will be, so we are dealing with a trace. Okay, the trace is only we care about ith entry of a matrix. Okay, we don't care what these 3 elements look like. Okay, so for a product, I will just calculate the elements in the diagonal, because we are talking about trace of resultant matrix. So I will just calculate the elements in the what I was saying, in the diagonal position P31, and then okay, so this was this, and now it is second row, second column. So it is B12, A12, B22, A22. Anyone who is doubtful about why I'm only calculating or don't worry about position of AIs and BIs, or let me be consistent. But A32, B32, and here it will be something which A13, A13, B13 plus A23, B23 plus A33, B33. Okay, and so trace of now, so A comma B is equal to trace of B transpose A, right? And we just calculate it will be what? A11. I want this to be 0. So A11, B11 plus A12, B12 plus A31, B31 plus this A12, or let me just copy this. And plus, okay? And this I need to be equal to 0 in order to B belong to the vector space. Please, if you feel lost at any moment, please let me know. Okay, I want this to be 0, but note that since A belongs to, not this, A belongs to S, this implies A11, A22 plus A33 is equal to 0. Okay, and S is set of all elements where the diagonal is 0. Addition of diagonal element, that is trace, is 0. So if I'm to talk about what BIs are possible, so we are talking about, so we have to find what these elements BI would look like. What are the possibilities of these BIs are? So let me consider this element. Oh, did I make a mistake? This is 2, 1. Yeah, 2, 1 is correct. If I take element A to be this 0, 0, 0, 1, and this. Okay. Then for any element B11, B12, B13, B22, B22, oops, not, we are in complement, right? B21, B31, B22. I'm just trying to do something. I hope you will get what I'm trying to do. 22, B, T2, B13, B, am I missing? Yeah. G21, B31, B21, B22. Let me write. I12, 13, 21, B31, B22, B32, B33. Really sorry for this. But yeah. And into if I do A 0, 0, 0, 1, 0, 0, 0, 0, 0, it will be just matrix with only entry possible this B12 and the rest is 0. Right? So if I write this trace of then if I do this A12 into B12, okay. I think this is not happening. But let me just tell you one thing. When we do this, the possibilities of AIs are anything. I mean, elements here could be anything, because these are off diagonal elements, not this one, this one, this, and this and this. These are off diagonal elements, and this could have any possibilities. Okay, and so we can choose elements A smartly such that we end up getting all other elements to be 0, and A12 and B21 has to be 0. I mean, we can choose AIs such that only A21, B12 is 0, and A2 is something non-zero, that is 1, B21, and we will get 0. Something of this sort we can obtain. And we end up getting that this elements B, A14, A17, these elements which are not at the diagonal becomes 0, and or let me do one thing. It is really confusing with 1, 2, 3s. I'm really sorry for this, but A1, let me do this because it will be then B4, B5, B6, B7, B8, B9, A1, A2, A3, A3, A4, A5, A6, A7, A8, A9. And then trace of this B transpose A will be just this A11, A1, B1, A2, B2, A3, B3, plus A4, B4, A5, B5, A6, B6. Not in this sequence, but addition will be this only. B7, A7, A8, B8, A9, B9. And we have A1 plus A5 is equal to A1 plus A5 minus plus A9 is equal to 0. So this will imply that A1 is equal to, or A9 is equal to A1 plus A5. And we can choose A's such that all these BI where BI is 0, where I not equal to 159. So all these elements become 0, and then in that case what we remain with this A1 B1 plus A5 B5 plus A9 B9 is equal to 0. Okay, and this will give me what? Since A9 is A1 plus A5 minus A1 plus A5, I will get A1 B1 plus A5 B5 plus minus A1 minus A5 B9 is equal to 0. And this will give me what? A1 into, B1 minus B9. Let me just finish writing this, and then I will try to solve your doubts. I hope I'm writing it correctly. Yeah, is 0. Okay, so if we choose A1 is equal to 1, A5 is equal to minus 1, then this B1 minus B9 minus B5 minus B9 is equal to 0 will give me what? B1 is equal to B5. And if A1 is equal to A5 is equal to 1, then I will get this B1 minus B9 minus B5 minus B9. And this will give me what? 2B1 plus. B1 plus B5 is equal to 2b9, but b1 and b5 are same. Then 2b1 is equal to 2b9, and this will give me b1 is equal to b9 is equal to b5. So all of them are 1. So see here, I chose this. When I do this, I am saying that I am taking this matrix A is equal to 1, 1, 1, minus 1, 0. And I'm accordingly adjusting my, trying to find what B1 and BIs are. What BIs are. Parameters for B1. Okay. I mean, what I'm saying is we can choose BAs from S such that we can get all the off-diagonal elements to be 0 for B, and everything in the diagonal has to be 1, 1, 1. Okay, so what we get that this S per actually becomes this 1, 1, 1, 0, 0, 0, 0, 0, 0, C in M3R such that C in R. So dimension of S per will be 1. That's what I was trying to say. So what I was saying is that since I assume that BIs are 0 and end up proving that B1, B5, B9 has to be equal, and I can choose AIs from S. I mean this A in S such that these off diagonal elements of B will become 0. I will give that explicitly to you if possible in the discussion forum if possible. But right now, please understand that dimension of this is equal to 1. I know it's a bit difficult because we are dealing with 9 variables as such. Because when, just example, let me show you earlier where we actually calculated V per, yeah, not for this. Somewhere we calculated it for 2 elements, right? B1 and B2. There it was only 2 elements set. But what we are doing here is, yeah, here. So we were dealing with only A, B, and C. A, B, and C. So we could manage, it was linear system in 3 variables and so on. But now we are no longer in linear system. We are in product of 9 variables and so on. So that becomes a bit tedious, but if you try to find the explicit elements from S such that you will get B4, B7, B8, B2, B3, B6 of B to be equal to 0, and we end up getting this B1 is equal to B5 is equal to B9, and dimension of S per, that is orthogonal complement of this set S, where S was 3 cross 3 matrices which stress A is equal to 0, then yes, dimension becomes 1. Please let me know if you have any doubt. I know you have many, but we'll just try to clear at least those which we can possibly clear. Hello. Have we seen last part? Okay, last part is this. Okay. No, ma'am. Whatever you said, watching. Okay. Okay. So let me tell you one thing. What I just said that if I have this B1, B2, B3, B4, B5, B6, B7, B8, B9, and if I take this element 0, 1, 0, 0, 0, 0, this, then what I just get is that, or not 1, A1. Okay. Then A1, I need to take complement of this. B, B2, B3, B4, B5, B6, B7, B8, B9. Okay. Then, and here it was A2. Then B2, A2 is 0, right? This trace of this thing, I want to be 0. This implies what? B2 and A2 to be 0. But A2 is anything in R, right? A2 could be this element A belongs to M3R. So this implies what? B2 is 0. Similarly, if I remove, I can take same. If I copy this. And now if I take here 0 and here I take A3, then this becomes A3 B3 is equal to 0, where A3 in R. So A3 could be anything. So this gives me B3 is 0. This is element A belongs to M3R. Okay. So doing this, similarly for A4 and so on, we get that. Okay, so all these elements become 0. And if you continue to do that, I mean, I guess you will get that B3 has to be 0 and so on. And you will end up getting elements which satisfy certain condition. And so eventually you will get this B2 is equal to B3 is equal to B, I guess 8 is equal to B4 is equal to B7 is equal to B6 to be 0, and B1 is equal to B5 is equal to B9 is equal to 1, and S per becomes this as I already written like this. C where C in R3. I hope you got the point. We will choose elements from space such that I can get rid of all the possible BIs to be 0, and then I calculate. But note that when I do this, for example, if someone says this, that A4 and A1 here is 0 and A1. If I do this, then this matrix is no longer in A. Okay, I mean, if somebody wants to say that I can just do now B1 A1 is equal to 0, and this implies B1 again 0, this is because since A1 is in R, then this is not true. Because now this matrix doesn't belong to my S. So I'm not talking about S anymore. I mean, am I making sense to those who are listening? I mean, we can do this for B1, B5 and B9, but we can do this. Trace must be 0. Exactly. Trace must be 0. So when we are finding orthogonal complement, the trace of B transpose A needs to be 0. And in order to do that, I have to find all these values. And you can see that when you smartly paste these AI BIs, you get BIs to be 0 for this 2, 3, 8, 4, 7, 6. And B1, B5 and B9 has to be 1. Because as soon as I put element here, A1, I at least need to put minus A1 and so on here. So in short, this A1, A5, A9 must be 0 and so on. So I hope I am making sense now. At least it is better than what I was saying earlier. Any doubts?
And how dimension you are telling it is 1?
because it is a matrix, right? We have 3 elements, it should be 3.
Only one element, sir. This is the basis of S per. Beta is basis of S per. So, and cardinality of beta is 1. Therefore, dimension of S per is 1. Is it okay? I mean, it is in M3 cross 3, but it has dimension 1. Is it okay? I mean, after looking at this too, I guess, this thing, this and this, you got the idea that this off-diagonal elements will be 0. And for diagonal, what we did was this. This thing will follow for diagonals. Bi is 0, where I is not equal to 1 to 5. So if you go and I will reshuffle the notes for this, and you can see, but yeah, dimension will be 1, that you can trust me on. Okay, is it fine now? Okay, great. Now is it clear why this is like 3 cross 3 element, I mean matrix of order 3 cross 3, but dimension of the vector space is 1 because it is generated by only one element, this 1 1 1 and 0 0 0 and so on.
So in short, we're
Okay.
saying there would be no other vector which give you the trace, or no other element in this which will give you trace 0.
Which will give me trace 0. Yes, because that is not possible. That's what we just did actually. Yeah, because what we have is when we are taking this B transpose A, trace of B transpose A, it is of this form, right? A11, A1 B1, A2 B2, C2 D2 and so on. So rest has to be 0 because we can choose this kind of elements and we are getting this off diagonal entries are zeros for B. And for trace, it is we just did here, right? A5 into anything and so on. This.
So we want to get the final calculation is A1 plus A5 minus A9. Then only I'll be able to get 0 here.
Yes,
Okay.
yes.
And for that to happen, I want B1, B5, and B9 to be 1.
Yes,
and rest I can do it as 0. Okay.
Yes. So
Okay,
when I'm
got it.
writing this, I'm actually considering this element. This is actually trace of B transpose A, which is this, which I want to be 0, where A is this actually. A1, A5, A9, 0, 0, 0, and so on. Okay. So when I take this element in S, so when I take this element in S, what does this mean? That A1 plus A5 plus A9 is 0. And then these calculations give me that once I have this, B1 is equal to B5 is equal to B9. And when I take this kind of elements of this, I mean, this kind of matrices, like I don't know how to highlight, I mean, this kind of matrices, then off diagonal entries are turning out to be 0. I mean, that's what it is. Is it okay? I mean, I will reshuffle the notes so that you will be able to understand it properly. Please go through it. Okay, and I hope this is clear now. If you have any doubt, please, you can ask me in the next session. That's not a problem. Okay, is it okay? Any further doubts? Oh, I mean, if there are no doubts, then we can stop for now here. And please put the questions in the discussion forum if you have any, and I will rewrite the notes for this last question and I will submit it in the portal and so on. Okay, thank you. Yeah, sure.